as Q is equal to rate of heat flow in a particular direction, whereas Q dash is the total heat flow in that direction. So Q dash is nothing but Q multiplied by dt, where the dt is the time interval. Okay, and then we have started the calculation of part A. Okay, so first we have discussed that the heat is entering inside the element from x direction, and total amount of heat entering inside the element will be nothing but rate of heat transfer multiplied by time interval. So rate of heat transfer, which is uh, uh, rate of heat transfer, is minus k suffix x multiplied by a multiplied by dt divided by dx. Okay, dabba t divided by dabba x multiplied by time interval for which we want to find out the total heat transfer. Okay, so q dash x we have calculated. Further we discuss about the area of the abcd face is equal to the dy multiplied by dz. Now during the same time interval, amount of heat will transfer from the element to the next element or to the surrounding by conduction. Okay, so that we have notified as a q dash x plus dx. Okay, so during the same time interval dt, heat flowing out of the right face of a control volume. Okay, efgh. So in same direction, which is the face, efgh is the face. Okay, according to our nomenclature, efgh is the face which is opposite to the abcd. So in x direction through EFGH phase, how much amount of heat is transferred to the another element or to the surrounding by the conduction. So that we have notified as q dash x plus, suffix x plus dx. So which is equal to change initial heat and in that particular direction and change in that particular heat. Okay, so initial heat entering inside the element is q dash suffix x, and change in that heat when it is traveling through the distance of a dx. Okay, so uh, small elemental change we have considered as the derivative of a q dash x, and the total, if you want to find out the total, then we have to multiply with the total length. Okay, so dx is the total length in the x direction. Okay, then further we have to find out the net heat accumulated. Okay, net heat accumulated means what? How much heat is entered in the element and how much heat is leaving. The difference between these two heat will be provide you the net heat accumulated inside the element. Okay, so that will be notified as a dq dash. Okay, dq dash suffix x for the x direction. Okay, which will be difference between the heat entered in the element through x direction and heat leaving the element through x direction. Okay, through x direction. Okay, the difference between these two heat will provide you the net heat accumulated in that particular direction. So dq dash x is equal to q dash x minus q dash x plus dx. Okay, so we have done the subtraction. So q dash x will be cancelled, and where dq dash x will be equal to minus dabba of dabba x of q dash x multiplied by dx. Okay, just put up next in next step we have just put up the equation of a q dash x, and we will get this equation. Okay, further this minus minus sign will be cancelled or it will be converted into a plus sign. Okay, so we'll get the equation of a dq dash x is equal to dabba of dabba x, or the differential with respect to x of k suffix x multiplied by dabba t divided by dabba x multiplied by dx dy dz multiplied by dt. Okay, we'll get this equation. Similar fashion, we have to find out the equation for dq dash y and dq dash z. Just change the coordinate, you will get that equation. Okay, so that will be the Roman 1 equation, and the Roman 2 will be normal 1 will be the equation for the x direction, net heat accumulated in x direction, whereas normal 2 equation. Okay, so we are considering it for the y direction, net heat accumulated in y direction. Just change the suffix accordingly where it is required. Okay, so dq dash x, instead of that we have considered dq dash y will be equal to dabba of dabba y, or differential with respect to y of k suffix y multiplied by dabba t with respect to dabba y multiplied by dx dy dz multiplied by dt. Okay, in a similar fashion, in the z direction, dq dash suffix z is equal to differential of k suffix z multiplied by dabba t divided by dabba z with respect to z, multiply by dx multiply by dy multiply by dz multiply by dt. We will get these three equation. The addition of these three equation will provide you the net heat accumulated in the element in all directions. Okay, so we have done the addition. Okay, addition of these three equations, equation number 1, equation number 2, and equation number 3. We reach up to this particular point. Okay, so addition we have done. We have added three equation 1, 2, 3, and we will get this equation. Okay, everybody written this equation up till now? Is there any problem, any question, any doubt? Okay, so further we have done the addition. Okay, we have added this equation, and in the next equation we have taken the common part of these three parts. Okay, three parts of equation we have taken the common. Okay, which is common in three parts of equation, that is dx, dy, dz, dt are the common in three parts of equation. Okay, so we have taken it outside the bracket. Okay, and we have written this equation. Okay, so equation will be dabba of dabba x into bracket k suffix x multiplied by dabba of dabba x bracket complete plus dabba of dabba y multiplied by k suffix y multiplied by dabba t of divided by dabba y plus dabba of dabba z or differential with respect to z of k suffix z multiplied by dabba t divided by dabba z bracket complete, and common thing out of these three parts of equation we have written outside the equation, that is dx multiplied by dy multiplied by dz multiplied by dt. So which is our A equation. Okay, or we called it as a part of a energy balance equation. Okay, this is the A part of a energy balance equation. Okay, getting everyone? Now next we have to calculate the B part of equation, that is the heat generated by the element. Okay, heat generated by the element. Now here what we have to consider, we have considered in the in diagram also q suffix g. Okay, q suffix g, small q suffix g. Okay, small q suffix g is equal to total heat generated per unit volume per unit time. Okay, we are going to consider one parameter, that is small q suffix g, which is equal to total heat generated per unit volume per unit time. Okay, write down once again. You can write down with me. Calculation of B, total heat generated within the element. Total heat generated within the element. Here we are considering one or we are assuming one significance or one nomenclature, that is q suffix g is equal to small q suffix g is equal to total heat generated per unit volume per unit time. Okay, per unit volume per unit time. Okay, so here if you consider that q dash suffix g is the total heat generated. Okay, capital Q dash suffix g is the total heat generated. Okay, volume of the element is dx multiplied by dy multiplied by dz. Okay, and time interval is dt. Okay, so the total heat generated, okay, total heat generated or q suffix g is equal to total heat generated divided by volume divided by time. Okay, so total heat generated is q dash suffix g divided by dx, volume is dx multiplied by dy multiplied by dz, volume of the element multiplied by time interval dt. Now just here we need to find out the total heat generated only. Okay, we have to find out the total heat generated. Okay, so that is nothing but we are focusing on q dash suffix g. Okay, we are focusing on q dash, capital Q dash suffix g. Okay, that is the total heat generated. Okay, so total heat generated, it will be q dash, capital Q dash suffix g is equal to, now if you want to find out this part, then we have to transfer the denominator in opposite side. Okay, denominator in opposite side. So we will get the equation for total heat generated as q dash, capital Q dash suffix g is equal to small q suffix g, that is the heat generated per unit volume per unit time, multiply by its volume. Volume of the element is dx multiplied by dy multiplied by dz. Okay, multiply by time interval dt. Okay, So that is our B part. That is our B part of the equation, that is net heat generated in the element or heat generated in the element. Okay, so write down the B part. B part, total heat generated, total heat generated within the element, total heat generated within the element. Okay, next line, next line. Small q suffix g is equal to, small q suffix g is equal to, small q suffix g is equal to total heat generated, total heat generated per unit volume, per unit volume, per unit time, per unit time, per unit time. So in an equation format we can write down small q suffix g is equal to, small q suffix g is equal to capital Q dash suffix g, capital Q dash suffix g whole divided by, whole divided by, whole divided by in bracket dx multiply by dy multiply by dz, that is nothing but the volume of element, dx multiply by dy multiply by dz, bracket complete, multiply by time interval dt. Okay, multiply by time interval dt. So next what we have to find out, total heat generated we have to find out. Okay, total heat generated with in the element we have to find out, that is nothing but q dash g we need to find out. Okay, so q dash g, total heat generated, capital Q dash suffix g is equal to, is equal to small q suffix g, small q suffix g multiply by, multiply by, multiply by dx multiply by dy multiply by dz, bracket complete, multiply by dt, multiply by dt, which is the part B of the equation, part B of the equation. Okay, so part B we have calculated. Now we are moving towards part C, that is the energy stored in the element. Part C is the energy stored in the element. Remember one thing, the total heat accumulated in the element due to heat flow along coordinate axis and heat generated within the element together serve to increase the thermal energy of the element. This increase in thermal energy is heat stored in the element. What it means? Okay, जितने भी हीट अंदर आ रही है और बाहर जा रही है, इन दोनों का डिफरेंस जो भी है वो डिफरेंस किस में रहेगा, एलिमेंट में ही वो डिफरेंस, वो जो डिफरेंस वाली हीट है वो एलिमेंट में ही रहेगी, और जो एलिमेंट हीट जनरेट कर रहा है वो हीट भी एलिमेंट में ही रहेगी. ओके, जो अंदर आई और बाहर गई और एलिमेंट ने जनरेट की, ये तीन पार्ट इंपॉर्टेंट है. उसमें अंदर आई और बाहर गई, इसका जो डिफरेंस है वो नेट हीट एक्यूमुलेटेड है, और एलिमेंट ने हीट जनरेट की वो पार्ट बी है. ओके, सो ये दोनों थिंग्स, ओके, नेट हीट एक्यूमुलेटेड एंड द हीट जनरेटेड बाय द एलिमेंट, ये दो जो पार्ट है वो क्या करेंगे, वो एलिमेंट की इंटरनल हीट बढ़ाएगी. ओके, थर्मल एनर्जी बढ़ाएगी. थर्मल एनर्जी बढ़ाएंगे मीन्स व्हाट, थर्मल एनर्जी बढ़ाएंगे मीन्स उसका टेम्परेचर बढ़ाएंगे. ओके, उस एलिमेंट का टेम्परेचर बढ़ाएंगे. ओके, सो दैट इज मीन्स व्हाट, द ये टेम्परेचर क्यों बढ़ गया, क्योंकि उस एलिमेंट में हीट स्टोर हो गई, इसलिए उस एलिमेंट का टेम्परेचर बढ़ गया. ओके, सो that is the significance of energy stored in the element. Energy stored in the element means what, the total heat accumulated in the element due to heat flow along coordinate axis and heat generated within the element together serve to increase the thermal energy of the element, together serve to increase the thermal energy of element. This increase in thermal energy is heat stored in the element. Okay, this increase in thermal energy is heat stored in the element. Write down everyone. Calculation of C, calculation of C. Energy stored in the element, Calculation of C. Energy stored in the element. Energy stored in the element. Energy stored in the element. In that, write down total heat accumulated. Total heat accumulated. The total heat accumulated in the element. Total heat accumulated in the element due to heat flow. Due to heat flow. The total heat accumulated in the element due to heat flow along coordinate axis along coordinate axis and heat generated within the element and heat generated within the element and heat generated within the element together serve to increase the thermal energy of the element. Together serve to increase the thermal energy of the element. Okay, this increase in thermal energy together serve to increase the thermal energy of the element. Full stop. This increase in thermal energy is heat stored in the element. This increase in thermal energy is heat stored in the element. Okay, so formula for heat stored in the element is heat stored in any body is equal to, you have discussed, you have dealt with this particular formula in thermodynamics also. Okay, heat stored in any body is equal to mass of the body is equal to mass of the body, write down mass of the body multiply by specific heat of the body, multiply by rise in temperature of the body, Okay, that is nothing but mcp delta T. You know this formula, mcp delta T. Okay, heat stored in any body is equal to mcp delta T, mass of the body multiply by specific heat of the body multiply by rise in temperature of the body. Written equation. Okay, so we can write down heat stored in any body is equal to mass we can write in the form of a density and a volume. Okay, mass we can write in a form of a density and a volume. Okay, so density of the element we are going to consider it as a rho. Okay, and the volume is equal to dx multiplied by dy multiplied by dz. We know density is equal to mass upon volume. Okay, density is equal to mass upon volume. So that formula we have converted here into a mass formula, Okay, so mass will be equal to density multiplied by volume, Okay, so if you consider the density rho and the volume of the element is nothing but dx multiplied by dy multiplied by dz. Okay, multiply by specific heat of the body. So specific heat we have signify as a C. Okay, capital C you can write. So multiply by C, multiply by rise in temperature of the body. Okay, rise in temperature of the body. Now this rise in temperature will happen with respect to time. Okay, rise in temperature will happen with respect to time. As the time changes, the temperature also goes on changing. Okay, so small incremental change we have written here as a delta T divided by delta T. Okay, rise in temperature with respect to time. Okay, small incremental change in time with temperature with respect to time. And if you consider, if you want to find out the total rise in temperature, then we have to multiply with the total time. Okay, so the rise in temperature in a small time interval multiply by the total time interval for which we are going to consider this particular equation. Okay, so dabba t divided by dabba small t. Dabba t is the change in temperature, okay, and dabba small d is the change in time. Okay, change in time. So change in temperature with respect to time. Okay, and total time interval is capital dt. So we have multiplied with the capital dt. So we will get the rise in temperature of the body for particular time period. For particular time period. Okay, so we'll get the equation: heat stored in any body is equal to rho multiplied by dx multiplied by dy multiplied by dz multiplied by capital C multiplied by dabba T divided by dabba small t, that is the rise in temperature with respect to change in time, multiplied by total time period as a dt. Okay, so this is the part C of the energy balance equation. Part C of the energy balance equation. Okay, write down this part C of the energy balance equation. Rho multiplied by dx multiplied by dy multiplied by dz multiply by capital C multiply by dabba t divided by dabba small t multiply by dt. Okay, getting everyone? Getting everyone? So now further we have to put up this part A, part B and part C in equation number Roman 1. Okay, equation number Roman 1 is the energy balance equation. A plus B is equal to C, and we have evaluate the A part, B part and C part for the volume element. Just we have to put up the part A, part B and part C in equation Roman 1. Okay, equation Roman 1. So the part A is the net heat accumulated inside the element. Okay, net heat accumulated inside the element, and that we have calculated as differential with respect to x, partial differential with respect to x into bracket k suffix x multiplied by dabba t divided by dabba x bracket complete plus partial differential with respect to y into bracket k suffix y multiplied by dabba t divided by dabba y plus partial differentiation with respect to y of partial differentiation with respect to z of k suffix z multiply by dabba t divided by dabba z bracket complete, whole bracket complete, and we have taken common from this particular bracket in equation number A as dx multiplied by dy multiplied by dz multiplied by dt plus part B, that is the heat stored in the element. Okay, so part B is the q suffix g multiplied by dx multiplied by dy multiplied by dz multiplied by dt, and the part C, just now we have discussed about the part C, which is equal to part C. Okay, A plus B is equal to C. So C part is rho multiplied by dx multiplied by dy multiplied by dz multiplied by C, that is the specific heat of the body, multiplied by change in temperature with respect to time multiplied by total time, that is dabba t divided by dabba small t multiplied by dt. Please write down this equation. Now put equation A, B, C in equation number Roman 1. Okay, in equation Roman 1. In equation Roman 1. Okay, so note down this equation, complete equation. Complete equation. Okay, over. Then further, we have to divide by dx, dy, dz multiplied by dt throughout the equation, because this is the common part in three part, or the common thing in three parts of equation. Okay, first part it is also dx, dy, dz, dt. In second part of the equation also dx dy dz multiply by dt, and in the third equation also dx multiply by dy multiply by dz multiply by dt. Okay, so we can divide dx multiply by dy multiply by dz multiply by dt throughout the equation, okay. So write down, divide both sides of equation, divide both sides of equation, divide both sides of equation by 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 dx multiply by dy multiply by dz multiply by dt. Okay, or divide both sides of equation by dx multiply by dy multiply by dz multiply by dt. Okay, so further after dividation, what we will get? Okay, after dividation we'll get this particular equation. Okay, after dividation we will get this particular equation. Okay, so partial differentiation with respect to x of k suffix x multiply by dabba t divided by dabba x, okay, plus partial differentiation with respect to y of k suffix y multiply by dabba t divided by dabba y, bracket complete, plus partial differentiation with respect to z into bracket k suffix z multiply by dabba t divided by dabba z. Okay, bracket complete, plus q suffix g is equal to rho multiply by c multiply by rise in temperature with respect to time, that is, or the change in temperature with respect to time, that is dabba t divided by dabba small t. Okay, dabba t is for incremental change for temperature, whereas dabba small t is the incremental change for the time. Okay, incremental change for the time. Okay, so have you written this equation? After dividing both sides of equation by dx dy dz multiply by dt, we will get this equation. Okay, so further we know some vector rules. Okay, we know some vector rules that here if you consider that the differentiation of I with respect to x plus differentiation of j with respect to y and differentiation of k with respect to z will provide you a del operator, So the equation, our equation will become a squeeze in a small equation if you use this particular del operator for this particular equation. Okay, so remember one thing, differentiation of x, differentiation of I with respect to x, differentiation of j with respect to y, and differentiation of k with respect to z. Okay, so where I, j, k are the points, or we can say that the coordinates on x, y, z axis. Okay, coordinates with respect to x, y, z axis, and this will provide you a del operator. So here also in our equation we are partially differentiating this particular part, okay, that is k in general k multiply by dabba t divided by dabba x, and this part we are differentiating with respect to x, with respect to y, with respect to z. Okay, so instead of these three differentiation, we can use the del operator here. Okay, we can use the del operator here. Okay, also this thermal conductivity k is varying with respect to axis. Okay, so or with respect to direction, so kx, ky, kz. So the del operator we have applied for this particular term, okay, complete term. Okay, k and dt divided dabba t divided by dabba x, k and multiply by dabba t divided by dabba y, k and dabba t divided by dabba z. So we have applied this particular del operator to this complete term. Okay, so here one del operator we have initiated. Now another thing also there, that the temperature is also changing with respect to axis. Inside the bracket it is changing with respect to axis. Okay, so change in temperature with respect to x, or partial differentiation with respect to x, partial differentiation of temperature with respect to y, and partial differentiation with respect to z. Okay, or incremental differentiation we can check it as. Okay, or consider it as an incremental temperature difference. So now So this is also changing with respect to axis. Okay, so this vector terminology we can apply for the temperature also. Okay, this vector terminology we can apply for the temperature also in this particular equation. So we will get the equation as del operator of K multiply by del of T. Okay, del operator of into bracket, del operator into bracket, K multiply by del operator T for T. Okay, plus, and remaining equation as it is, plus Q suffix G, Q suffix G is equal to, rho multiply by C multiply by dabba T divided by dabba small t, dabba T divided by dabba small t. Getting everyone how we have converted this equation into this format? Okay, for that purpose we have to take the help of this del operator. Okay, vector del operator, okay. Getting everyone, is there any question, any doubt? So write down these two equation. After dividation of dx multiplied by dy multiplied by dz multiplied by dt, we'll get this equation. Okay, this equation. And after getting this equation, we have to apply the del operator for this part. Okay, which part? This one, first part. Okay, we can say that the first part. For first part we are applying the del operator. Okay, so outside the bracket, first we are applying the del operator outside the bracket. Okay, and next we are applying the del operator for the temperature change. Okay, next we are applying the del operator temperature change. So this bracket is changing with respect to the axis. Okay, what it means, this bracket is changing with respect to axis. Also the temperature is also changing with respect to axis. Temperature is also changing with respect to axis. Okay, so del of K multiplied by del T plus Qg plus Q small q suffix G equal to rho multiplied by C multiplied by change in temperature with respect to time. So that is dabba T multiplied by dabba small t. Okay, so that is our equation number Roman 2. That is our equation number Roman 2. So this is called as a general heat conduction equation. This is called as a general heat conduction equation. Remember this important equation, general heat conduction equation. Write down the equations, general heat conduction equation. Is there any question, any doubt up till now? General heat conduction equation. Okay, is there any doubt, any question? Whether you understood or not, please comment in the chat box. Great, great. Have you written? Shall we move ahead? Okay, so further, now there are different forms of a general heat conduction equation. Okay, we have written this general heat conduction equation for the three-dimensional conduction, or we can say that three axis we have considered. So for that purpose, this is a three-dimensional equation. Further, it is deduced in a different format. Okay, and for that purpose, we need to apply different conditions. Okay, according to condition, format will be changed. Okay, so different forms of heat conduction equation. First form, okay, general heat conduction equation for constant K. So constant K means what? Isotropic material. if the thermal conductivity or the property of a substance is same in all direction, then that particular material is called as a isotropic material. Okay, isotropic material. Initially, we have considered that the material is anisotropic. Anisotropic means what? The property of a material changes in every direction. In x direction, there is a different thermal conductivity. In y direction, there is a different thermal conductivity, and in z direction, there is a different thermal conductivity. Initially, we have considered that in x direction it is k suffix y, in y direction it is k suffix in x direction it is k suffix x, in y direction it is k suffix y, and in z direction it is k suffix z. Now here further modification we have to perform in this equation, that if you consider that the material is isotropic material, that is thermal conductivity of a material does not change with the direction. Okay, in that particular with the axis, the thermal conductivity is constant. Okay, so that is our assumption, and on that basis we have modifying our general heat conduction equation. So consider k suffix x is equal to k suffix y is equal to k suffix z is equal to k. Okay, so that is means what? The thermal conductivity is constant. Okay, k suffix x is equal to k suffix y is equal to k suffix z is equal to k. Okay, so if you consider this, okay, so instead of k suffix x, k suffix y, k suffix z, you can write only k. Okay, you can write only k. Okay, so write down our general heat conduction equation before applying the del operator. We know that this is our general heat conduction equation. Before applying the del operator, okay, we are going to consider the same equation only. Okay, we are going to consider the same equation only. Okay, consider this equation. Partial differentiation with respect to x of k suffix x multiplied by dabba t divided by dabba x, or partial differentiation of t with respect to x plus partial differentiation with respect to y of k suffix y multiplied by partial differentiation of t with respect to y plus partial differentiation with respect to z of k suffix z multiplied by partial differentiation of t with respect to z, bracket complete, plus qg, q suffix g, that is the heat generated per unit volume per unit time, is equal to rho, that is density, multiplied by c is the specific heat multiplied by change in temperature with respect to change in time, that is dabba t divided by dabba small t. Okay, now in this equation what we have assumed that kx is equal to ky is equal to kz. Okay, so instead of kx, ky, kz, we are going to put up only k. Okay, so we'll get the equation partial differentiation with respect to x of k multiplied by partial differentiation of t with respect to x, bracket complete, plus partial differentiation of y, partial differentiation with respect to y of k multiplied by partial differentiation of t multiplied by t, or partial differentiation of t with respect to y, bracket complete, plus partial differentiation with respect to z of k multiplied by partial differentiation of t with respect to z, bracket complete, plus qg is equal to rho multiplied by c multiplied by dabba t of dabba small t. Dabba t, that is change in or rise in temperature with respect to rise in time or change in time. Okay, we have done this. Okay, then further we can take the k common from this particular bracket. Okay, from this bracket we can take the k common. Okay, thermal conductivity common, as it is constant with respect to direction. So k will be the constant now. Okay, k will be the constant now. Okay, it is not changing with respect to axis. So we have taken k common, or we have taken k common from this particular bracket, and we will get the equation as k multiplied by into bracket partial differentiation of x, or we can say that double derivative we are considering. Okay, differentiation of x in bracket differentiation with respect to x of a bracket in bracket the temperature change with respect to x plus differentiation of with respect to y of temperature change with respect to y, and differentiation with respect to z of temperature change with respect to z, plus qg is equal to rho multiplied by c multiplied by dabba t divided by dabba small t, dabba t divided by dabba small t. Okay, now we have taken the k common. Okay, now what we are going to do, we are dividing by k throughout the equation. Okay, we are dividing by k throughout the equation. So next step is divide by k on both sides, divide by k on both sides. Okay, divide by k on both sides, divide by k on both sides. Divide by k on both sides. Over. Now after dividation, okay, so we have to divide k throughout the equation. Okay, so here the k will be removed from this particular term or the part of the equation. First part of the equation, k will be removed. Then next, second part is qg, so it will be divided by k, qg divided by k, or you can write qg multiplied by 1 by k also. Okay, here for the sake of understanding, in equation format suffix will not be there in word file, so I'm not getting how to write down the suffix in equation format. So for that reason, I have written over here qg multiply by, you can say qg multiply by 1 upon k. Okay, qg multiply by 1 upon k is equal to rho multiply by c multiply by dabba t divided by dabba small t multiply by 1 upon k. Okay, what we have done, we have divided, we have divided throughout the equation by k. Okay, divided by k on both sides, we can say that divided by k on both sides. Okay, so further we'll get this equation after dividation. Write down the equation. Or now further what we are going to do, okay, so this is a double differentiation, okay, or double derivative. So we are merging these two derivative as a double differentiation with respect to x, with respect to y, and with respect to z. Okay, so here we have written this dabba 2t divided by dabba x square plus dabba 2t divided by dabba y square plus dabba 2t divided by dabba z square. Okay, so that will be double differentiation of t with respect to x, double differentiation of a t with respect to y, and double differentiation of a t with respect to z. Okay, we are merging these two differentiation. Okay, we are merging these two differentiation. Okay, plus qg, q suffix g multiply by 1 upon k, or you can write qg divided by k, no problem. Okay, qg divided by k, q suffix g divided by k is equal to rho multiply by c multiply by dabba t divided by dabba small t multiply by 1 by k, okay. Okay, in this step we have just merged two differentiation outside the bracket and inside the bracket, because it can be converted into a double differentiation format. Okay, double partial differentiation we can say. Okay, now once again we can apply the vector operator. Okay, so here the double differentiation is there, or double derivative, partial derivative is there with respect to x, with respect to y, and with respect to z. Double differentiation or partial double differentiation with respect to x for the t, double differentiation with respect to y for the t, and double differentiation with respect to z for t. Okay, so we have applied the vector operator, and we will get the equation as del square t plus q suffix g multiplied by 1 upon k, or q suffix g divided by k is equal to rho c divided by k. We have merged these three parts in one form, or in one term. Okay, so that is rho c divided by k, multiplied by dabba t divided by dabba small t, dabba t divided by dabba small t, dabba t divided by dabba small t. Okay, getting everyone? Now further, one more term is introduced in this particular we can say that the equation, that is nothing but the thermal diffusivity. Okay, remember, alpha is equal to thermal diffusivity, and it is equal to thermal conductivity divided by thermal capacity. Okay, divided by thermal capacity. Okay, K is the thermal conductivity. We know that K is the thermal conductivity, and rho C, rho multiplied by C, that is the density multiplied by specific heat, is called as a thermal capacity. Okay, is called as a thermal capacity, and thermal conductivity divided by thermal capacity is called as a thermal diffusivity, and the nomenclature for the thermal diffusivity is alpha. Okay, nomenclature for thermal diffusivity is alpha. In the next lecture, we are going to understand the significance of a thermal diffusivity. Okay, so but here the terminology come inside the this derivation. For that purpose, we are interpreting that terminology, that alpha is equal to K divided by rho multiplied by C, K divided by rho multiplied by C, which is equal to thermal conductivity divided by thermal capacity. Rho multiplied by C is nothing but density multiplied by specific heat. Density multiplied by specific heat is called as a thermal capacity. Okay, thermal capacity. Okay, so thermal conductivity divided by thermal capacity is called as a thermal diffusivity. Is called as a thermal diffusivity. Okay, now in our equation, it is the inverse of K divided by rho C. That is nothing but rho C divided by K. Okay, in our equation, it is the inverse of alpha. That is rho C divided by K. So our equation will be modified as del square T plus Qg multiplied by 1 upon K, or Qg divided by K is equal to 1 upon alpha multiplied by dabba T divided by dabba small t. Okay, or change in temperature with respect to change in time. Change in temperature with respect to time. Okay, getting everyone? What is meant by alpha? Alpha is called as a thermal diffusivity, and its formula is K by rho C. Okay, where K is the thermal conductivity and rho C is called as a thermal capacity. Okay, rho is density of the material and C is the specific heat of the material. It is once again, it is the property of a material. Okay, it is a property of a material. Thermal diffusivity is also a property of a material, like thermal conductivity. Okay, so alpha is equal to thermal diffusivity, and accordingly we have modified our general heat conduction equation. Okay, we have modified our general heat conduction equation. Instead of rho C divided by K, we have introduced 1 upon alpha. Instead of rho C divided by K, we have introduced 1 upon alpha in this equation. Okay, so del square T plus Qg divided by K, or Qg multiplied by 1 upon K is equal to 1 upon alpha multiplied by dabba T divided by dabba small t. Q the equation number 3 for this particular equation. Equation number 3 for this particular equation. Okay. Equation number 3 for this equation. Getting everyone? Is there any question, any doubt? Okay. Have you written everything? So further, next form of this general heat conduction equation. Here, what we are going to consider in case of no internal heat generation. Okay. Up till now, we are considering that the element is generating the heat. Okay. Element is generating the heat. So we are considering it is the element of any wire, or we can say that any heater. Okay. Any heater. Okay. So if you pass the electric current through that particular heater, then that elements of that particular heater will generate the heat. Okay. That is our general assumption up till now. Now, if you consider that if that element does not generate the heat, okay, if that particular element does not generate the heat, so what will be the equation, general heat conduction equation for that particular element? So in that case, we have to assume that Qg is 0. That is the heat generated per unit volume per unit time is equal to 0. Okay, heat generated per unit time, per unit volume per unit time is equal to 0. That is small q suffix g is equal to 0. Now we are going to substitute this Qg value in our equation number 3. Qg value in equation number 3. Okay, so our equation 3 becomes, what is our equation 3? Del square T plus Qg multiplied by 1 upon K is equal to 1 upon alpha multiplied by dabba T divided by dabba small t. So in this equation, if you put up small q suffix g is equal to 0, then this term becomes 0. This term becomes 0. So equation 3 becomes del square T is equal to 1 upon alpha multiplied by dabba T divided by dabba small t. 1 upon alpha multiplied by dabba T divided by dabba small t. Dabba T divided by dabba small t. Okay, getting everyone? If that particular element does not generate the heat, in that case, the general heat conduction equation, how we have to modify that particular general heat conduction equation. So in that case, q suffix g is equal to 0, and we have to put up 0 instead of q suffix g in the equation, and we have to modify the equation if internal heat generation is not there for the element, okay, or for the material. So if you write this equation in an enlarged form, or we have removed this del square operator, okay, del square operator for the t, then we can write down the equation in a general format, okay, general format as dabba 2t divided by dabba x square plus dabba 2t divided by dabba y square plus dabba 2t divided by dabba z square is equal to 1 upon alpha multiplied by dabba t divided by dabba small t. Okay, this equation is called as a Fourier's equation. This equation is called as a Fourier's equation. Remember this equation is called as a Fourier's equation. You can consider this equation also and this equation also. Both the equations are valid one. Just we have removed out the del operator, and we have written the equation in an elaborate format. So this is also a Fourier's equation, and this is also a Fourier's equation. Okay. Is there any doubt, any question up till now? Write down all the things. It will be useful for you to understood this particular subject, this particular chapter, and further if you want to uh, make your career in a software, okay, like ANSYS Fluent or CFD Computational Fluid Dynamics, then these things are very much important. Okay, these things are very much important, and there is a large scope for such softwares in industries. Over, everybody? Is there any doubt, any question? You can put up your roll numbers in the chat box if you don't have any doubt. And the remaining part, that is further forms of a general heat conduction equation, we will discuss in the next lecture. Okay. Remaining students, please put up your roll numbers and you can leave the meeting.